Alright, so we've got a video lesson here we're working on tonight. And today we're talking about rate of change. Alright, so we talked about the other day that we know that derivatives have a number of uses. Alright, and obviously the first one is what we were studying in that first section, that the derivative is the slope of the line that is tangent to a given function at some particular point. Alright, well, the second application of derivatives is velocity and acceleration problems. So I'm sure you guys that have been in AP Physics have a good chance of having used this at some point. Alright, so let's just get a little bit of common terminology or discussion here. Position function. We're going to abbreviate that as S. Alright, the position function is defined as it's the position as compared to the origin, or as compared to the x-axis, how high something is. Alright, that's what we're talking about. We're talking about the height of an object, either being shot up or falling down. But it's the position of an object as time, which we are going to symbolize obviously with t, as that time passes. So the idea here is we're talking about objects that are moving here, preferably moving up or down. So remember, distance equals rate times time. So if we manipulate that formula a little bit, and if we say that if rate equals distance divided by time, then we can find the average velocity, or the average speed, and we're talking about average right now. Okay, so make sure you're paying attention to that. We can find the average speed of an object by taking however much distance that it travels, and that would be denoted by the change in s, divided by how much time has changed, denoted by delta t. All right, so however far something has traveled divided by how long it takes to travel that would be your speed. All right. I kind of think of it as, if I'm on a graph, delta S is going to be controlled by my y values, how much it's moving up or down. And then delta t is going to be controlled by my x values, how it's moving left and right. And so that looks a lot like our slope formula that we've been working with lately. So let's look at an example problem here to kind of give you an idea of what we're talking about. So suppose that I'm standing on the top of a building and I drop a ball. All right, so let's say the building is 100 feet tall. All right, and that ball falls according to the following function. All right, so s of t. So remember, our position function with respect to time equals negative 16t squared. Alright, and we'll explain where that negative 16 comes from down the road, plus 100. Maybe you can guess where that 100 comes from right now. So according to that function, alright, that's how the ball is going to move. I want to find the average velocity from the first second that the ball has been dropped to the second that the ball has been dropped. Alright, so what's the average speed during that time? So what I'm going to do is I'm going to plug 1 in for t. Alright, that's our first second. And when I plug that in, that's going to give us a value of 84 feet. And that'd be 84 feet above the ground is what that means. That's where the ball is at t minus 1 second, or t plus 1 second, I guess you should say. It's 84 feet above the ground. And then I'm going to plug in 2. And as I plug in 2, I got a little bit more work here to do. I got to square my 2. I got to multiply that by negative 16. So negative 64 plus 100 is going to give me 36. So it's 36 feet above the ground at that point. So you can see that ball has dropped, approximately 50 feet or so. So my change in S would be 84 minus 36. And my change in T would be 1 minus 2. Right? Because I have to make sure that I'm consistent with my coordinates, if you will. All right, 1 goes with 84 and 2 goes with 36. So 84 minus 36 is 48, and 1 minus 2 is negative 1, and so I get negative 48 feet per second. That's a rate, that's a velocity. It's negative. Why? Why is that a negative rate for? Hopefully it's because you understand, because the ball is dropping. All right, it's going to the ground. All right, so my average velocity, right? So understand what that means. Over the course of that 1 second, the average speed is negative 48 feet per second, which is great. But man, there's a lot more to the story than average velocity. All right, that velocity is not constant. It's changing. All right, whether you're driving a car or dropping an object or throwing something, that velocity is changing the whole time. All right, so with calculus, we can start to try to understand instantaneous velocity. That means velocity at any particular moment. And that's something that you could never do with algebra techniques. All right, but with a little bit of calculus, we can start to calculate what velocity is at any particular moment. All right, so to do this, let's think about this a little bit here. Our velocity, all right, can be found by doing a limit problem as delta t gets close to 0. So think about what we're saying there. Delta t gets close to 0. So the distance between the first time we take and the second time that we take gets really, really close. All right, and so this is that slope formula that we've been working with for the last few days. All right, that's that change in position of the first time that we take minus the change in position of the second time divided by that change in time. All right, so those are changing in positions divided by change in time. So what we're saying with this, if you understand what that limit problem looks like, what we're really saying is that the velocity function is the derivative of the position function, right? That formula is what we used to find the derivative in the previous section. All right, so velocity is the first derivative of position. Gotta try to let that soak in a little bit. Maybe pause and go back and look at that if you need to. So let's try an example of this and see if we can try to put this into practice a little bit. So suppose we've got a diver, all right? So like in a swimming competition, you got a diver that jumps from a platform 32 feet above the water. That scares me just to think about that, but let's just, for argument's sake, pretend this is actually going on here. All right, so you got a diver that jumps from the platform 32 feet above the water. All right, so his position function, or her position function, all right, would be represented by negative 16t squared plus 16t plus 32. Again, we'll talk more about what those coefficients mean and where they come from, and you can try to start to figure it out as well as you go through these problems. So the first question I'm going to ask is, when does the diver hit the water? All right, so what does that mean? Translate that in terms of this math problem. How would you determine when that happens? How do you figure out when the diver hits the water, mathematically speaking? Well, mathematically speaking, it would be when your position function equals 0. 0 would be the height of the water, if you will. So we're going to let our position function equal 0, and we're going to solve that for t. I'm going to divide all of these terms by negative 16, just so that coefficient in front of my t squared is far easier. That makes a lot easier looking quadratic here that I can factor into my two binomials. I've got t minus 2 and t plus 1, which yields two solutions, setting them equal to 0, t equals 2, t equals negative 1. So I'm not really sure what the heck negative 1 means. That would mean that he hit the water 1 second before he jumped, which doesn't really make any sense in the context of this problem. So this gives us one solution. The diver hits the water 2 seconds after she dives. All right, so after she jumps, she's going to hit the water 2 seconds later. All right, we find that just by setting that position function equal to 0. All right, so my second question now is going to be, what was her velocity at the moment she hit the water? What was that instantaneous velocity the moment of impact. So again, translate that. Right? How do we determine that through mathematics? What does that mean? Well, it's just going to mean what was her velocity at t equals 2. All right, that's when it happened. So the first thing I'm going to have to do is find my velocity function. So remember, just a few moments ago, we said that velocity is going to be the derivative of the position function. All right, so our position function, remember, was negative 16t squared plus 16t plus 32. So my velocity, using those rules that we learned yesterday, is going to be negative 32t. We're going to take 2 times 16, reduce the power by 1, plus 16. All right, 1 times 16, and now the t is gone because it's t to the 0. Now that we have that velocity function, we go ahead and plug in 2. So negative 32 times 2 plus 16 is going to give me negative 48 feet per second. Again, it's negative. Why? Because the diver is going down as they hit the water. Alright? So what I want you to do now is this. I want you to take a look at this problem here. Alright? A ball is thrown straight up from the top of a building. The height of the ball is modeled by this particular function. You've got 6 questions here. Alright? I'd like you to push pause here in just a moment. Alright? And try to work on these problems. Do the best you can either by yourself or with a partner, but push pause now and work on those. Alright, so you've had a chance to work on them. Hopefully you drew some pictures. Hopefully you could figure out whatever it is you need to figure out there. Alright, here are my solutions now to the problem. Okay, so for question number 1, alright, it's asked, what's the height of the building? Alright, so height of the building is just going to be when t equals 0. That's where the ball is at t equals 0. So I plug 0 into the position function, and you notice that coefficient at the end, that's going to be the height of your building. We call that the initial position. So if you want to jot that down somewhere in your notes, that's the initial position. The building is 96 feet tall. Alright, question number 2. Alright, when does the ball hit the ground? So we just did this problem with the diver idea. So we're going to set the position function equal to 0. And again, we'll go through the algebra needed to get t by itself. And we'll get 2 solutions again for this. T minus 6, t plus 1, which gives us t equals 6, t equals negative 1. Alright, negative 1 again doesn't really make a lot of sense. So the ball hits the ground 6 seconds after I throw it up into the air. Alright, 6 seconds of hang time, if you will, before that ball hits the ground. Okay, so that's question number 2. Again, if you need to stop, go back, look at these a little bit. You can always pause and rewind this as you need to. Question number 3. Find that velocity when the ball hits the ground. That's referred to in like physics as the terminal velocity. Alright, what's the velocity at impact? So my velocity function is negative 32t plus 80. Just use my derivative for that. I plug 6 in because it was 6 seconds before it hit the ground. That's going to give me negative 112 feet per second. Again, negative 112 because that ball is going down and going down in a hurry at the moment that it hits the ground. Okay, negative 112 feet per second. Alright, question number 4. Alright, what is the initial velocity? So what was the velocity the moment I let go of the ball? So again, that's just me plugging 0 in, right? 0 seconds, that moment I let go. And that's going to give me 80 feet per second. And now that's a positive number, so that means I threw the ball up into the air. It was going up away from the ground. Question number 5. Tough one here. When does the ball reach its maximum height? And then what is that height? So I want you to think about this picture right here. All right, as I throw that ball up, it's going to go up, 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 and then it reaches that point where it doesn't go up any higher and it falls back down. At that point where it kind of stops just for a second, if I was to draw a tangent line right there, that would be a horizontal line, which would mean that the slope of the tangent line would be 0. So think about that for a second. Slope of the tangent line is the derivative. So if I set our derivative or our velocity function to 0, I should be able to figure out when that happened. All right? So if I set v of t equal to 0, and I solve that for t, I get t equals 2.5. What does that mean? It means that 2.5 seconds after I let go of the ball, it reached its maximum height. And so now if I take that 2.5 and I plug it into my position function now, right? Because position always tells me where is that ball relative to the ground. If I plug that into my position function, it will tell me how high it was when that happened. And so after you do your work for this, you discover that that was 196 feet above the ground. All right, that thing went up to a height of 196 feet. Now I didn't throw it 196 feet up. I was already 100 feet up, but it reached a maximum height of 196 feet 2.5 seconds into the throw. All right. I think this is a tricky one, but it's a very important one. So make sure you get this, how to find that maximum height. This is a big application of using derivatives right here. When you get that changing behavior in your function, it's not going up anymore, now it's coming down. So based on that, how do I find the average speed of my ball? So remember, average speed is going to be the change in position, right? The change in distance divided by the change in time. So if I started 96 feet up and I threw it 196 feet above the ground, it went up 100 feet. Obviously it fell 196 feet. So disregarding direction, because those are both positive numbers, they're distances, I add those together and the ball traveled 296 feet through the air. How long did it take to do that? Well, remember our delta t was 6 seconds, right? It took 6 seconds before the ball hit the ground. Average speed is just those two numbers added or divided by each other. So 296 divided by 6 is going to give me that average speed of 49.3 feet per second. Now remember, that's just an average. It really is very few times during that flight that it actually was moving at that speed. But that's the average speed the whole entire time. So using what we did here, try to get some practice problems done here. I'll give you on page 282, numbers 85 through 88, and we'll talk about these tomorrow. All right? Thanks.